Let's prove triangles are congruent by ASA and AAS. The angle-side-angle congruence postulate says that if two angles in the included side of one triangle are congruent to the two angles and the included side of a second triangle, then the two triangles are congruent. Here's what that means. We've got our angle, we've got our angle, we've got our second angle, we've got our second angle, and the included side being that one that's right in the middle of those two angles. If we have that set up, then we know that those triangles are congruent to one another. And for the angle-angle side, same thing for the angles. We've got one set of angles. We've got two set of angles congruent. But this time it's not the side that's between the angles. It's one of the other sides that is congruent. That's called a non-included side. Two angles and a non-included side, congruent to two angles and a non-included side. That's an angle-angle side. And this one's a theorem because we have enough that we could prove this one. I found this example of how the military used to locate ships out at sea in the World War I and World War II times. They had two towers positioned on the shore, and they had a pre-measured distance between those two towers. So they knew that that length was fixed. And then when they sighted a ship out at sea, they could measure the angle between the other tower and the ship they saw. So from each tower, they were measuring the angle between the ship they saw and the other tower. And so what that set up was an angle-side-angle situation. And because they had enough information to know that that triangle was fixed, they could pinpoint exactly where that ship was located using math. So I thought that was a neat example of the angle-side-angle congruence postulate. Here are just some structures that are marked and they want us to try to figure out if we could prove that these are congruent. So this first one, do you recognize what I think that looks like? Does that look like a bow tie to you? When you see a bow tie, do you remember what I told you to look for when you see a bow tie? Those vertical angles. So if you see a bow tie, you can always put in your own vertical angles being marked congruent. Now they already had some of the markings on there. I can see that they had ticks here and here, and they had swoops already up here and already up here. So that's all the markings that we have. We added our own vertical angles, so what do we have there? Remember that you always want to cover up one of the triangles when you're trying to decide what kind of order you're looking for. Do you see that on each triangle we're looking at two angles and one side? So this is either angle side angle or angle angle side. You just have to decide where the side is positioned. Is the side positioned between the two angles, or is the side positioned kind of just next to one of the angles? And I would say the side would have to be between the angles if it was right there. So this is more of an angle-angle side because that side is just sitting next to one of the angles. And if we checked out the other triangle, it's the same situation over there. So this would be an angle-angle side example. This umbrella is looking sort of like a bow tie too. It already has those angles in the center marked. Actually, it has all of its angles marked. This is looking like an angle, angle, angle to me, right? But wait, have we had an angle, angle, angle congruence theorem? We actually haven't. It turns out that those two triangles would not have to be congruent. It's actually possible to have two triangles that aren't congruent at all, whose angles match up perfectly. So angle, angle, angle doesn't mean that the triangles are congruent to each other. Do you remember what I always want you to look for? I want you to look for bow ties, and this is an example of it, shared sides. Do you see how those two triangles are sharing that middle side? And what happens when they're sharing a side? We can say that that middle shared side is congruent to itself using that reflexive property, right? And then we already saw that we had a swoop up here and a swoop down here. And we saw that we had a double swoop in there, kind of hard to see, and a double swoop in there. And so I think we've got two angles and a side on both of those. If I cover up one of those triangles, let's think about where's the side positioned. Is that side positioned between the two angles? Or is the side positioned only next to one of the angles? I'm seeing this angle here and this angle here, and that side is right between the two of them. I'm thinking this one is an angle side angle. It's the included side. It's the side that touches both of those angles. And it's always a good idea to check the other triangle too. Same situation there. That side that's marked is between the two angles. That side is touching both angles. So that is definitely angle, side, angle. So those two triangles would be congruent to each other. Let's try a quick little proof. CE is perpendicular to BD, and angle CAB is congruent to angle CAD. Those are my givens. And we're actually trying to prove that those two little green triangles are congruent, so I just shaded those in for us. First thing, do those look like they're a bow tie's worth of triangles, or do they have a shared side? And I am seeing a shared side. How about you? Those two little green triangles are sharing side AE, are they not? So I think that's where I'm going to go first. I'm going to take the easy point that side AE is congruent to side AE because of the reflexive property. And that gives me one set of congruent sides. And did you notice I didn't put a little A up here? That was on purpose because that set of angles isn't actually in the green triangles. But actually there is, it's a little tricky, but there is a way that we can say that since those angles outside the triangles are congruent, we can say that these angles inside the triangle are congruent. It's a little tricky, but give me a chance. So here's where I think I can claim that those are congruent. Would you agree that these two angles over here are supplementary since they're a linear pair, and these two angles over here are supplementary since they're a linear pair? That's just the linear pair postulate. And there's this old theorem that says if two angles are supplementary to the same angle or to congruent angles, then they are congruent to each other. And that's what I just claimed, is that they were congruent to each other. And that old theorem was called the congruent supplements theorem. So I kind of crammed that all into one. So again, this is a little more tricky than I'd expect you to do on your own. That was a combo of the linear pair postulate and the congruent supplements theorem. But I got myself a pair of congruent angles. And I used that given. You might have noticed I haven't used the perpendicular given, but oh, I plan to. I've got that little right angle right there. And wouldn't this other one also have to be a right angle? Because if I have perpendicular lines, then I have all kinds of right angles, right? If perpendicular, then 4 right angles. That's theorem 3.9. And now I've used that given, and I've got myself some right angles. Right angles are good if I'm using hypotenuse leg, but I definitely don't have a hypotenuse marked congruent here. I think I better say that those right angles are congruent to each other. What allows me to say that right angles are congruent to each other? The right angles congruence theorem. And now I've got a pair of congruent angles. Is everybody seeing that I have two angles in one side? Now I just have to figure out what order it is. Is it AAS or is it ASA? Because that's going to be my final step that shows that those triangles are congruent. I've got those markings with the angle, and the side. And that side is the one that connects those two angles together, right? And so we would say that that side is included between those angles. And so the side is included between those angles. And so this is the angle side angle congruence postulate that proves those triangles are congruent to each other. And let's get our pink sheet updated with the angle side angle congruence postulate. And the angle side, that one's a congruence theorem. Not too concerned that you say postulate versus theorem. I won't even pay much attention to that. And then on the flip side, let's make a little diagram for each of those. An angle side angle. Again, we would have an angle marked congruent to a corresponding angle. We would have another angle marked congruent to a corresponding angle. And which side am I going to mark congruent? It's the side that is positioned right between those two angles, the one that touches both angles. It would have to be this included side. Let's make one for angle side. Let's use those same two angles. This angle is congruent to this angle congruent to this angle. And we want the side that we choose to really only be touching one of those angles. We could either choose this one right here or the bottom one. Both of those would be an angle side setup. And we have now finished all 5 triangle congruence postulates and theorems. It's almost like a multiple choice game now. Every time you're proving that triangles are congruent, it's going to be because of one of these 5 reasons. These are the only 5 reasons we would ever use to say that triangles are congruent to each other.